Welcome back on another session on RLC circuit. In my previous video, I looked at the output voltage across different components of the circuit and derived the differential equations for that. In this video, we'll be looking at the same circuit but using the Laplace transform or the S domain. So we'll be working in the S domain instead of the time domain. So the equations remain the same. First equation here is the summation of the voltages, because this is a series circuit. The current, since this is a series circuit, this is the current through the capacitor. Here, this component here is the initial condition, so the initial charge stored on the capacitor. For now, we'll assume that this is zero for the rest of this analysis. And using this equation, we can find the voltage across the capacitor, which is 1 over Cs times the current. Similarly, the voltage across the inductor is Ls I of s minus the initial condition, which we'll also ignore. Then we can substitute these two equations into the voltage in summation equation and have this equation here. From this, we can extract I of s, which is the common factor, and simplify this equation further, where we get one equation for the current. So this is an important equation here. It gives us one common equation for the current, and we can use this to calculate the voltage output across different components. The first one we'll consider is the voltage output across the capacitor. So that is the voltage output across the capacitor is 1 over Sc times I of s. So this component here is the capacitive reactance, and we just need to substitute I of s that we have worked out already. Once we do that and simplify, we are left with this equation, which is the transfer function of this system if we take the output voltage across the capacitor. We can use this equation to analyze a bit more of the properties of this circuit. So we can say, okay, at f equals 0, so if the input signal is 0 Hertz or it's a DC, then the transfer function, we can substitute s equals 0 and we get 1. So that means the input voltage is equal to the capacitor voltage across the capacitor, which is the output voltage. So what this is saying is, if you apply a constant voltage across the capacitor, the capacitor will charge up to that input voltage. So it will store charge. At the other end of the spectrum, if the frequency was very high or infinite, then the transfer function becomes 0. So then the voltage across that capacitor would be 0 volts. And we can sketch that in this rough approximation. And this is a low-pass filter, which means this circuit is able to allow any low-frequency components to pass through, but it will block any high-frequency signals. So just to look at it in more detail, so the capacitive reactance is 1 over 2 pi Fc. So again, at f equals 0 Hertz, which is a DC signal, the capacitor acts as an open circuit. So if you substitute f equals 0 here, the reactance becomes infinite. If the capacitive reactance is infinite, then there will be no current flowing through it, which means the voltage across the capacitor is equal to the input voltage. So you're essentially charging up the capacitor at this point. Now, if the frequency is very high, it's a high frequency signal, maybe an AC signal, then the reactance capacitive reactance will be 0. If you substitute infinity here, this will be 0, which means the capacitor will now act as a short circuit. So the current will be maximum flowing through it. What this means is the two plates of the capacitor, when there is a high frequency signal applied to it, the electrons will go from one plate to the other at a very high frequency, which will result in a high current, i.e. which will be the maximum current that this circuit can support. Now, if we look at the next one, where we take the output voltage as the voltage across the inductor, we'll use the same current equation. This is a common equation since this is a series circuit. For that, it's again very simple. So the voltage across the inductor is SL times I of S. SL here is the inductive reactance. We substitute I of S, simplify that equation, and we get this transfer function. If we do the same analysis as before, if we apply a DC signal to this circuit, then the transfer function will be 0, which means the voltage across the inductor will be 0 volts. On the other end, if we apply a very high frequency signal, then the transfer function is 1, so the voltage output will be equal to the voltage input. So the voltage across the inductor will be the same as the voltage input. So this is behaving as a high pass filter. It allows any high frequency components but blocks any low frequency or DC signals. So if you look at the inductive reactance, so that's given by 2 pi FL. So when F is 0, the reactance is 0. So these two components are frequency and reactance in this case are proportional to each other. And the current flowing through it will be max. So this will act as a wire. On the other end, if the frequency is infinite, then the voltage, sorry, the inductive reactance will also be infinite, and hence the voltage across the inductor will be the same as the voltage input voltage, and the current will be 0. Now in this example, we are ignoring what happens to the capacitor. And finally, if you take the voltage output as voltage across the resistor, now a resistor is not a frequency dependent component. So what that means is its voltage or current does not depend on the frequency. So the voltage across the resistor is resistance times the current. So that's R multiplied by the current equation. So that's a very simple substitution, and we get this transfer function. And we can do this analysis, but this will behave as a high pass filter again. So this concludes this video. In the next video, we'll look at the transfer function in more detail and understand what sort of properties we can derive for a system using its transfer function. Thanks for watching.